Okay. So yeah, so we're starting. So just a quick recap. Last time we talked about tangent spaces, um, and we gave two definitions of tangent spaces. First of all, we defined them as yeah, collections of differential operators evaluated at p. So like v of f is equal to a sum of some coefficients times partial f of phi inverse partial x j evaluated at phi of p. And then the second definition we gave is that they are linear maps from the space of smooth functions on M to R that satisfy the product rule written there. And we proved that the first definition is equivalent to the second definition. Okay, great. Now, the first thing that I want to do today is do like a change of variables formula for these tangent vectors. So suppose that we have some charts on a manifold, phi and u and psi on v of m, such that we have some overlap here, right? It's not equal to the empty side. So let P be in this intersection of U and V, and let V be a tangent vector at TPM. Okay. By this first definition, we have that V is equal to some of AI's, or I'll use AJ's, of acting on F is equal to, again, AI times partial F of phi inverse partial xj evaluated F of P. We also have, by the same definition, but for the other chart, that this is equal to, again, a sum, this time of some coefficients bj times the partial derivative, the jth partial derivative of f of psi inverse evaluated at psi of p. So again, you have this manifold, and then you have two charts. This is u, this is v, and then you have some vector, some tangent vector here, and then it gets mapped kind of to sort of different vectors. You can think of this as different vectors in, well, yeah, vectors with different coefficients in Rm. So like the representation with respect to the local coordinates of phi of v is going to be like some vector A, where the components are the coefficients. And then with respect to psi, it's some other vector B. And here we want, we would like to write the
to point out, you have colors for all these diagrams that you could use.
Where?
Maybe drawing the different sets and different colors may be helpful.
That is true. Okay, let's say U will be blue, and then phi is also blue, and then A, sure. This will be green.
Also, maybe you want to put primes on one of the x's and.
I suppose that is true. I mean, they're technically the same operator, but
Yeah.
whatever. Yeah. I mean, yeah, whatever. So, right. We want to write BJ's, or equivalently this vector B, which has components BJ, as or in terms of the AJ's. So the way that you do this is that you observe. Let's see.
Hey, hold on. Do people understand what the question is or what the problem is or what we're trying to do?
No? Okay. So again, suppose you have two charts, right? And then they intersect. The two charts have some intersection. Now you pick a point. You pick a point P here in the intersection. Okay. At the intersection, you consider the tangent space, and you pick like any vector in the tangent space. So clear so far? Okay. So by the first definition, we have like a local coordinates representation of this vector with respect to some coordinate chart, right? This representation depends on phi here, right? Because it depends on phi. Now, therefore, you have like two different representations for phi and psi, right? These are different coefficients here, because
where one you write in one set of coordinates, another one you write in a different set of coordinates.
Yep. So yeah. And so we want to somehow relate this set of coordinates to this set of coordinates, or like vice versa. We want to know like what one is in terms of the other. So like BJ is some function of AJ somehow, right?
And so let's look at a very simple example. Suppose my manifold was just, R2 itself.
So yeah.
At some point, I have a tangent vector. Okay? Now suppose I then gave the same R2 coordinates, but these coordinates are like rotated coordinates. Okay? In these coordinates, a vector that looked like this is going to look different, right? And so the question is just how do you go from writing the vector in one set of coordinates to another? That's all this is.
So that's
Yeah.
this one very simple example, right? So here's what we'll do.
So small tip: if you write something down and then you immediately erase it, you might as well not written it down.
I don't have a space though.
That's true. Then maybe write it down somewhere else.
Okay.
Or just don't write it down.
That's well. Okay. So yeah.
So you can fit it up there.
Yeah.
Yeah. Okay.
Yeah.
Great. Right. So here's what we're gonna do. Notice that this is essentially just the same as D, or the Jacobian. Yeah, let's write D. I mean, technically, we're gonna have like a different D later, but it's fine. This is yeah. This local representation is equal to the Jacobian applied to phi minus 1 at 0.5p. And then you apply a to it, where a is the coordinates a1 through am. It's these coefficients. So because this is, again, what is this? This is an n by 1 matrix, or this entire thing is an n by 1 matrix, which approximates f of phi inverse whatever. This is just d dx1 of phi, or f of phi inverse, blah blah blah. these are the partial derivatives, right? And so you just multiply this matrix by this vector. Does that make sense so far? Okay. Now I'm going to write. D of f of phi inverse is the same as d of f of psi of psi of phi inverse. Okay?
Hold on.
Yeah.
Are you composing psi with psi? You need an inverse?
Oh, yeah. Psi inverse. Yeah. Yeah. That's correct.
So maybe additionally gesture what that looks like on the diagram.
Right. That would look something like
I start where?
you start with this, the image of phi, or yeah, and then you go. Let's use orange. So yeah, so you go back to here. Now from here, you apply phi, so you go here, and then you go back because phi inverse, right? And then you apply f to it, which is the same as doing like going back here and applying f, right? Which would be f of phi inverse. Okay. Yeah. So anyway, I'm doing nothing here. Okay. I'm essentially this is whatever. And then at phi of p, and then we apply a. Right. So I'm gonna break this down into two functions. And then we know that this is a diffeomorphism just by the definition of transition maps and atlases. This is, smooth again also by definition, so we can just apply the chain rule, and then we get that this is equal to d. Let's see, f of psi inverse evaluated at, and then you take psi of phi inverse of this, which is phi of p, and this cancels out. And then composed with d of psi phi inverse, the transition map, evaluated at phi of p, and you apply a to it. Right. So, and so. From our previous considerations, when we said that like v of f is equal to, or this sum is equal to this, similarly, v of f, just instead of like phi, you take psi, it's going to be equal to d of f of psi inverse of psi of p with b. This is just like the same logic that we used to get this from this, but applied to this. Okay, so like this gives us this. Now, what we're gonna notice is that like these two things have the same form, and in particular, this is the same as this b. Okay.
How is that the same as this b? Oh, I see.
Yeah, because like this part is the same. This part is the same between the two. And so we apply, like the same. Yeah.
Okay, so then write down what is b in terms of a.
So yeah, and from this we get that b is equal to this thing, d of psi of phi inverse at phi of p and then you apply A to it. So that's yeah.
My brain's a little lost. We're gonna what we should have done is like whatever we did formally with phi, we're gonna do with psi now. And in the the final formula which you've written out here, the first term should be the same for both A and B.
The first term is the same.
Jacobian matrix.
The first, yeah. So this matrix is the same. And so like, you know, these coordinates are the BJs that we're looking for, because we want to write BJs such that essentially this works.
Oh, sorry, my bad. I thought we had to do them replace, like you slot in identity there. So my bad, I get it now. Okay.
This df composed with psi inverse or phi inverse, whichever one. That's just a f is a function. Yeah, f is just a function, right?
Yeah, but I thought you were gonna like slot it in an identity and then put phi inverse in there.
I mean, that's what we already did.
I mean,
on this side, we're not gonna do
There.
it over there, right?
we're not gonna do it
Okay.
over. No,
We
no,
don't
no,
need to- We've already done it.
Yeah, yeah.
no. Yeah.
I get it. Thank you.
And so you get what? You get that if you want to take the derivative of the function f, you take the derivative, and then to do it kind of in the right direction, you need to apply, like, add the following bj coefficients, right? Or aj coefficients, depending on which coordinates you're in. If you're in the first coordinates, okay, you just apply the vector a, and then you get the right coefficients. But then if you wanted to do it for psi, okay, you need df composed with psi inverse there instead of phi inverse. So you just add psi and phi inverse. And so you see that the coordinates are now a applied to that matrix. And it's, you know, the same thing. Yeah.
So in essence, what we're doing is that we're to actually have an explicit transformation.
Between coordinate charts. That's it.
Yep.
All this was is if I have a vector field written, a vector written in one set of coordinates, how do I write it in a different set of coordinates? And it's kind of the obvious answer. You look at the transition map changing from one set of coordinates to another coordinates. Look at the Jacobian of that, which is literally a thing that kind of maps tangent vectors to other tangent vectors, and apply that to the vector you had in. Right? Remember, D kind of mapped df is a linear map. It maps best linear approximations here to best linear approximations here. And so that's what it did. A was gave you in some sense some best linear approximation. In a different coordinate chart, you just use D of that transition map to get D.
Maybe I'm tripping a little hard. How can we split D into the functions?
Chain rule.
Thank you.
And so this important is that f with psi inverse and psi with phi inverse, they're functions from Rn to Rn. So there we know what's going on in each.
Okay. I'm gonna erase this now.
Yeah.
Yes.
Maybe turn everything
You
Mhm.
could also
Uh,
you have more space. You can pull it to the side.
oh, it's whatever. It's fine. We don't need this anyway. I mean, we do, but it's fine. Okay. So, a couple definitions. First of all, we say that a map F from a manifold M to some other manifold N is smooth if for all P.
So if I have time,
Yeah.
the claim is I'll write up some exercises. Will you just practice, like, you know, writing vector fields in different charts? There's surely exercises in the book.
So right, we say that a map F between manifolds is smooth for if for every point in M. Let's see, there exist charts. So phi u, it's a chart of M, and a chart psi v of n such that, let's see, we have pi belongs to u. We have that f of, or p belongs to u. F of p belongs to v, and in fact, I suppose this is unnecessary, but whatever. The entire image of u under f is a subset of v, and let's see, and we have that phi of f of or psi of f of phi inverse, which is a function of real variables from phi of u to psi of v, is smooth. Okay. Yep, it's clear. And then another definition, we say f is a f between, I suppose I should say we write f belongs to C infinity of m comma n. That's the notation. So if f is smooth, a function f which is smooth is also called a diffeomorphism if if it has a smooth inverse. Oh, yeah. Oh, sorry.
What do I need to add to make it called the diffeomorphism?
Yeah.
The inverse of 17.
What do you mean? Just like?
Oh, just f.
No.
It should be that. It should be some function carrying you from psi of v to phi of v. It's
Oh, you don't have to. Well, I mean, like, okay, you can talk about like the charts, but there's like a simpler way.
So you have a function from m to n which is defined, that just maps points on sets of points to set. And we say it's smooth that if you take a chart from psi and take a chart from phi, then that kind of composition is smooth for any chart. But the function exists, independently.
oh, that's it. Well, the diffeomorphism, if you can take the inverse of that, and the inverse is also smooth.
Yeah, exactly.
You can always take f inverse.
Well,
if f is invertible.
Well, if
you
f
can
is
take f
invertible,
inverse
yeah.
without reference to chart.
Okay. Right. So that's wonderful. I think we are in position to talk about the tangent map. Are we? Not quite. Okay. So first of all, I want to talk a little bit about pullbacks and push forwards. So if we have a smooth map between manifolds from M to N, then we can sort of pull back certain mathematical objects from N to M, and similarly push forward certain mathematical objects from M to N. So like, and the notation, and this will become clear in a second, is we say that f with a star in the upper corner is a pullback, and then f with a star in the lower corner is a push forward. And so this is defined differently for various objects. A simple example would be if I have a function. So let's say I have g belonging to this would be C infinity of n. Yeah. Then I can pull it back, and this is written f pullback of g by composing it with f. And this is going to be a smooth function of m, right? Because f is, this goes from m to n by f, and then from n to r by g, okay? So in total, this is a map from m to r. Yeah?
Stop and yeah, maybe draw a picture
Yeah, okay.
with just like the same thing with circles. Just draw a bunch of circles with arrows.
Right. Do we have space?
Right below.
You could also pull the board to the side.
Yeah, okay, let's pull the, actually, you know what, no, I don't like that. Let's draw, I'm gonna draw a little picture. It's gonna be small, but it's fine. So I have a manifold, two manifolds in fact, and then like R. So yeah, this will be our N, and this will be our M. And then I have G defined. G takes points of N to R, okay? F takes points of M to N. We can compose, you know, doing like this, F, or G of F is going to take points of M to R. And because both of these are smooth, because F and G are both smooth, it's also smooth.
And so the statement is that before I had some function G on N, but then I used F to pull it back to a function on M. Do you agree? Does that make sense? And do you remember?
It's called a pullback.
That's why it's called a pullback. Do you remember where we saw this in linear algebra? The exact same notation.
Dual.
Yeah, the exact same notation in linear algebra, but maybe we didn't talk about it too much. What's one thing that in linear algebra we like should have talked about but didn't have time to, and so we didn't really discuss it? Dual spaces, that's right. And in dual spaces, what did you have? You had a linear operator, T, between V to W, right? Then you had this dual operator on the dual spaces, but it went in the opposite direction. And it was doing like essentially that. There was some linear functional on whatever n was. Okay, so you had like a function g on n, and you could, if you had a map between m and n, you could pull the linear function back onto m. So pullbacks usually act on like something that's like a function or a vector field or something like this.
We'll see examples. So this is a function getting pulled back. Similarly, you can kind of, if you have a curve, just as an example, let's say I have a curve, gamma, that goes, it is a smooth curve on M, right? Then I can compose it with F by doing, let's see, so yeah, F of gamma, and this is going to take me from J to M to N, and so this is going to be a curve on N, okay? So similarly, we have like, this is M, let's see. We're gonna have some interval J, and then this is gonna get mapped to some curve gamma on M, and then we can compose this with F, to get like some other curve uh, this is gamma or 5 or f of gamma here, which is some other curve on n. And this would be the push forward, written like this, of the curve gamma.
In general, you have to be careful. Like qualitatively, a pullback is like usually just like I pre-compose, and push forward I just like post-compose. But for different objects, there might be like some subtlety with how exactly you do this.
Yeah.
So you have to be a little careful, especially for the push forward. In the push forward, sometimes there's like I don't know, there's something that I always forget about. But the pullback usually is just like I pre-compose in some natural way.
Okay. So we've talked about, pullbacks of functions. We've talked about push forwards of curves. We can push forward vectors, and that's what the tangent map does. I'm going to erase this now.
Yeah.
This is meant to map, like it's called a tangent map because it maps between
Exactly. Yeah.
So this is something that I was like kind of alluding to in my drawings on day one, where I could start at a point and I could walk in some direction, and then I was looking. Suppose I was mapping out say f. The best linear approximation tells me how to kind of walking in this direction. What direction does that correspond to walking in here?
Okay.
And we're going to see that.
Right. The definition is as follows. So let f be a smooth function between two manifolds, right? The tangent map written. I'm gonna use df. God, I should probably consult my notes. Because I forgot to specify a point. Let p be a point on M. The tangent map written df at p is, and I'm gonna just say this, a linear map between, well, let's do this. Yeah. T p of M, and then it sends it to vectors at in the tangent space at f of p in n given by let's see. So we have this map, right? We take a vector, and then we get another vector, so we have to think about like the action of it on some function, and this is equal to v of or I'm using f here, of f. I suppose g would be better here. Let's use g. Yeah. And so, this there are a couple things to.
Let's give people a moment to think, and then maybe ask the audience some questions.
Right.
So, where is V defined on? Where is V on?
tangent space of V.
Of points
Exactly,
V
yeah.
and M. Okay. And so, what does V? Remember, what kind of object is V? What does it do? Someone else. What does V do? V is a tangent vector, right? What do tangent vectors do? What was the tangent vector from last time?
Oh no. Okay. No.
At the beginning, we were showing how to change coordinates for tangent vectors. What was a tangent vector? It's a direction, but
It's
in our particular case, we realized tangent vector should be the same as some other kind of object, which was what? In coordinates, it looked like what?
Your
Hmm? Yeah, but
derivative.
yes, derivatives.
Yes.
There we go.
Yeah.
Oh,
Remember,
wait,
tangent
question on
vectors.
that.
Yeah.
Yeah.
Last time we started with the definition saying, hey, you have this space which satisfies product rule with V.
Mhm.
Why now are we starting with the Jacobian matrix and then going to that? And
So-
not V going to Jacobian.
So this is a good point. This is kind of abuse of notation.
Yeah.
This DFP
So,
is where this is something else. This is not the Jacobian.
yeah. It's-
This is he just defined DFP to be this thing,
Specifically,
not the Jacobian.
in the book, they write TPF.
Yeah.
But then I was told by Ivan
I
that,
don't know. I
that
don't like TPF. And then
yeah.
what we're going to see in the end, we're going to see that this tangent map DF of P,
is
which is
essentially
something between tangent spaces. If I write it down in coordinates, it's going to just be the usual Jacobian in coordinates. But right now, this is not the Jacobian. This is
Okay.
some map from TPM to TFPN. Okay, so I had to take a tangent vector at point P. So it's like some way of taking derivatives at point P. And then I map it to some other way of taking derivatives at point F of P in kind of the target space. Okay. And so then, okay, what kind of object is V? V is something that takes in what? Taking derivatives. What does taking derivatives take in and out at a point?
Which coordinates?
No. You take derivatives of what? Of functions. Okay?
Yeah.
So V takes in as input a function and outputs at a point a number. Right? If you take a derivative, you at a point, you take in a function, you output a number. And it's linear on functions. Great. So V is something that takes in functions on M, and at point P it outputs you some number. Okay? Depending on the function you take. What we want to do is we want to take this vector V and push it forward to some vector at TFPN. Sorry, to some vector at the point F of P and N.
Yeah.
Maybe draw some like circles again.
So, so again, we have, let's see, M, we have N, we have some like tangent space, we have like this point, and then some vector V.
Yeah.
Okay.
And once again, a vector is like some derivative.
Yeah.
Yeah.
In local coordinates and okay, global coordinates is roughly the same.
And then we have a map F,
Yes.
and this takes it to F of B,
Yes.
surprisingly. And then we have a tangent map here as well.
Mhm.
And then we have a vector, and this is like, and this vector is DFP of V.
Yeah. Right. So I want to, before I was taking in functions on M and differentiating them. Now I want to use V to define something where I can differentiate, I can take in a function on N and then output a number and still satisfy product. Yeah.
But F is the map that carries you from M to N.
Yes.
Mhm.
Between F and DF. DF is the
DF
So
is this
F
map.
maps the points of M to N.
Mhm.
DF is going to map tangent vectors at a point, tangent vectors at a point.
it is a weird notation. I see.
Yeah.
So the book was going to use TPF to mean the map between TPM and TFPN, but we're going to see that this will end up being the same as the Jacobian we had before, and so we're gonna start with this notation. For now, it's different. Soon we'll see it's the same.
And the way we know it's different is because it's capital F and not like parentheses.
What do you mean?
Like before, when we talk about Jacobian, it's D of F.
Like no, the
No.
notation is exactly the same.
Yeah.
It's just it's
It's
contextual.
different because I'm telling you right now this means something different.
It's contextual. Like
Yeah.
if f was a function of real variables, then we would
Because
just have.
especially like if you wanted to be really pedantic, before for us, the Jacobian was mapping some vectors in Rn to some vectors in Rn. Now here we're talking about mapping like some object that takes in functions, outputs a number at a point, to some other object that takes in functions, outputs a number at a point. Now, when we wrote it in coordinates, we realized actually it's the same as a vector in Rn because I just need to specify like the coordinates, the coordinates of like in which direction I take the derivative, and that's the same then. Remember I had like ai partial xi, right? So I just need to specify ai's to specify a derivative in some direction, and that's essentially like a vector in Rn. So we'll see later that it's all the same, but for now it's slightly different. Okay, and now
Okay.
explain how we defined it.
Right. So you know, as we've been talking, this is essentially like taking a tangent vector in M or TPM and taking it to a tangent vector in N. And so we can think of this as sort of, again, using push forward notation, we can define the push forward of a vector. Yeah.
Is this not a pullback?
No, well, we're pushing forward the vector by pulling back the function.
Yes. Okay.
Yeah.
This is.
So we push forward the vector, again, as I've said, by pulling back the function, which is a fun little way
I feel like this is
to think,
confusing notation
I suppose.
and doesn't explain anything.
I suppose. Okay.
Look, you want to have what? You had something that takes in functions, outputs a number on M. You want something that takes in a function on N and outputs a number. But you only have something that takes in functions on M. So how do I use this thing on M? Well, I have a map from M to N. So if I was given a function on N, I could turn it into a function on M by pulling it back and then differentiate that. Okay, and that's what it's doing. It's telling you, okay, if you have some way of differentiating on M, and you want to get some sense of differentiating on N, that's fine. Just pull everything back onto M and differentiate on M. Okay, and that gives you a way of differentiating on N. Okay, and then we need to check that all of these things satisfy product rule and
Yeah.
yada yada.
Yeah,
But they do.
they do. They do.
You can check fairly easily.
Yeah. So yeah, that's the tangent map. Let's look at an example actually.
Yeah, I think
At a
it's
good
probably
example.
perfect.
I'm gonna do a couple examples. What kind of 1.5 examples? So let's say we have a curve, curve gamma. Again, from J to M, and then yes, and we of course we have F from M. Or no, that's not right. It's just gamma. It's just gamma. So we can think of an open subset of Euclidean space as like an n-dimensional manifold. So like in this case, this is a subset of R, an open subset of R. So we can think of this J as a sort of manifold of sorts, a very simple manifold, where the charts are just going to be the identity, and then you just have one chart that maps everything to itself, and then because it's Euclidean space, it works. And this is, let's say, a donut. And so we have some point, let's say t0 in J here. Let's so T0, and we think of the tangent space here, and again, because it's a one-dimensional manifold, the tangent space T0 of J is going to be exactly just the span of right, it's not even a partial because we're in one variable, ddt at T0. So, you know, you only have one variable, and you're differentiating with respect to that variable. And so we can think of, say, v equals exactly d dt at evaluated t0 or t naught, whatever. And then we can think of gamma as a function from j to, again, m, and this is like the curve. This is our actual gamma. It's gamma of t. And then we have gamma at t0 or t naught. And so this is our point, right? And then we think of the tangent map d of gamma at point t0 or t naught of our vector v, which we defined to be d dt at t0. And this is, in fact, going to be, let's see, this is going to be d dt of some function, which I forgot to write. Take some f or some g, I guess, to be consistent. This is going to be d dt of g of gamma evaluated at t naught. And this should look familiar, because this is exactly one of the definitions that we gave for a tangent space. I don't know if we didn't dwell on it too much, but essentially this is taking the derivative of g with respect to like the direction that gamma is going at t naught. Does this make sense? Because you know, gamma is like it's like a function that goes in a certain direction, and then you're taking the derivative with respect to that direction at a certain point.
So, okay, let's try and match this to the definition, right? What is, in the definition you had some map f. What's the map f in this case? What is m and n, and what is the map f here? Gamma is the map f, that's right.
M is j.
Is the interval, okay.
N is m.
N is, yeah, n is, you know, whatever that blob is, okay. And then I have a curve. And okay, I have some sense of, I don't know, whatever it is.
It's a donut. It is a donut.
It is a donut.
It is a donut.
And so I have some way of taking derivatives on J,
line,
right? On the line, that's just ddt. And after I map by gamma, I now get some way of taking derivatives on kind of the curve after I map by gamma, which is just by, you know, precomposing the function with j and then taking the with gamma and taking the derivative, right? If I have a function on the torus g, I can precompose it with gamma and get like a curve on the torus and just differentiate along the curve.
Precompose is like the full f.
Yeah.
Yeah.
Precompose is literally just like do
So like this is, again, this g of gamma is just like a function from j to r.
yeah, that's like gamma pullback of g.
Yeah.
But once again, gamma pullback of G is like a fancy way of saying pre-compose G with gamma, right? But pullbacks, so for functions, saying the words pullback is like, very fancy for seemingly no reason. But then you start getting objects that have like a lot more inputs, more that they take in more than just a point as input, like differential forms. And there, if you wanted to like, explicitly write down that you pre-compose everything in every possible entry, that's just too much writing. So instead use pullbacks. Okay.
Yeah.
So I think this is going to be a good example. I'm going to give the following as an exercise. You have some function on R2, right? And I'll give like a few specific functions, which are simple but maybe of interest. And then you have a particular curve that gets mapped into R2. And then differentiate those functions along the curve.
Because you know how to take dimensions in R2.
Well, in R2, you know how to take derivatives. It's much easier than like the simplest manifold ever.
There's 0 dimensional.
Yeah, well, even simpler, but then I don't think I have.
I don't know if you do.
You don't really have
Yeah.
derivatives because you don't have.
Well, it's like vacuously
Yeah,
easy.
yeah.
It's so easy that you don't even have to do anything. Okay. So that's one example. Right, and I'm gonna erase this now. And
But do people now understand how to do this mapping one tangent vector to the other tangent vector? Right. I want to differentiate functions there, and I do that by just differentiating them where I know how to differentiate.
I forgot to say something, I guess kind of obvious, but also important. This is, again, as we've said, is differentiating G in the direction of gamma. So this would be like the same as taking like the tangent vector to where gamma is going at this point. So that should maybe like give you maybe an intuition. It's the linear approximation to gamma at that point, in a sense, which is why it's similar to the Jacobian.
You'll show that
that's also, yeah, I'll show it. But then like this is like a way of, it's like showing it in this special case. But yeah, but now let's show it for Euclidean space, and then we'll generalize it to manifolds. How are we doing on time? Okay. Because, I mean, we haven't gotten to vector fields yet.
That's okay.
I don't know if I will be able. We'll have to like speed through it a little, but it's fine. Okay. Right. So, suppose, again, the special case, consider U in Rm open, and then an open subset V in Rm or Rn, and then F, a smooth function from U to W, or to V, right? Right, and we want what? Let me think for a second. And we want V belonging to like the tangent space at some point P in U. Yeah, for some T and U. And then we have V equals, oh my god, that's not right. We're gonna look at what happens at the basis vectors, and then we're gonna extrapolate that because TPF is linear or TF is linear. Yeah. So we're going to consider df of p, fix p. I should really be looking at my notes, but it's fine. Df of p of partial xj, which, so let's think about this for a second. So if I have TPU, right? This is like a tangent space of Euclidean space, right? My vectors here are going to be equal to like some combination of AIs d dx dxi's. Okay. And then we can sort of identify this as just taking like the Jacobian, like if I have a function f, then v of f is literally just like the Jacobian at p, and then you compose it with this a1 through am. And so, you know, like you can think of these as basis vectors, these d or partial xi at p is kind of like similar to the ith basis vector, because this is just applying the ith basis vector to the Jacobian or whatever. Oh, sorry. I shouldn't.
Right in front of it. No one behind you could see anything.
My point is essentially these are the basis vectors for the tangent space, these differential operators. So if we know how this map behaves on these basis vectors, then we know how it behaves for everything, because this is a linear map. Does that make sense? Okay. I'm gonna leave this for a second now, but because it's fine. So
you can maybe draw like a bubble around it, so that
yeah,
it's separated from the rest. Good.
So this is equal to, by our definition, let's see, compose it with some function. I'm going to use g, just keep writing f in the, and this is going to be equal to, let's see, d dxi of g of f at p. Nothing crazy so far. Or this is a j. Yeah, I want to keep this a j for indexing purposes later. And at this point, we do the chain rule. We do the chain rule. You do the chain rule, and then you get this. This is equal to the sum of this is going to be partial g partial x I times partial fj. Hold on, that's not right. Partial fi partial xj. And this is going to be, let's see, this is evaluated at point P, and this is evaluated, no, wait, yes, this is evaluated at point f of P. Is that right? I believe that is right. And this is equal exactly to, I'm just going to rewrite this in a nicer way. Yeah, whatever. Yeah. Yeah. P, and then d dx I at f of P of G. And then what we're going to notice is that d fi dx j at P is just the Jacobian entries at, I'm going to write f prime at P, and this is like the ijth entry.
Maybe write df.
Well, I don't want to write df because then it's like this, and then we're trying to find df,
Sure.
so it's like, so yeah, so like this essentially gives us, again, these are, so if this was the
take a step back
yeah.
and just give people a moment to
Yeah,
look
okay.
at it. Of like, what did we just do? Yeah.
It's an F prime or Fi?
So okay,
That's supposed to be
this
the
is
Jacobian.
fi, and this is f prime.
Okay.
Okay. That is, by f prime he means just the Jacobian
The
in the
Jacob-
old sense.
Mhm.
As like a matrix.
Oh yeah, because that thing.
Yeah. So why it's partial fi, partial xj, that's just the Jacobian in the old sense. And so what am I doing here? Right?
This definition matches with our old, like when we do this on subset on some like set M to N, it's the same as mapping with the Jacobian as our
We didn't show that it's the same. Well, yeah, yes. So we showed that right now that just for open sets Rm and Rn, right? That if we look at the f of P applied to partial xj, right? Applied to partial xj applied to some function g, right? So the f of P applied to partial xj, that should be some sense of taking a derivative. Do you agree? So let's apply it to function j. And so he writes what it is, applies it to function g. Sorry, not j, g, right? Okay, takes the derivative. And then I want to express what I get in terms of just taking derivatives of the function g at f of p. Okay? And I realize that, it's this partial xi of g with coefficients fi partial xj. So I see that partial xj got sent to partial fi partial xj times partial xi. And then I sum over the i's. So write this at the bottom. So just write down partial xj. Partial xj, like got sent to with an arrow. Yeah. And then write what it got sent to.
I'm gonna write
Just
Yeah,
write
whatever.
just write the sum. It's not that.
It is, well, uh,
Whoa, I wouldn't write that kind of derivative.
Yeah.
It's still a partial.
yeah.
Take a step back. Yeah. This is what we just computed. That gets sent to that in a linear fashion. And the Jacobian matrix is precisely this partial fi partial xj coefficient at the rate point.
So essentially, yeah. So remember how I said these differential operators are like the basis vectors?
Yeah.
So this is, if you apply the nth or the ith basis vector to a matrix, you're taking the column, right, the jth column. And then what we're seeing here is that you take the jth column, the coefficients are the jth column of the Jacobian times like these basis vectors in the output tangent space. So essentially, if we write kind of like df at p from like ddxi at p to ddxi at f of p, this is going to be the same as like just f prime at p with respect to the standard basis. That's what we proved. Okay.
And now, surprise, surprise. So this is something we did open sets of Rm to Rm. Right? Now we want to write something like this down for actual manifolds, right?
Yes.
So what's going to happen when we do this for manifolds? What's going to be the difference between writing it for this and for manifolds?
You need like a translation later?
The
Yeah,
charts,
we're
yeah.
just going to need charts. Then we're going to write everything down in charts. In charts, I'm going to once again get functions like maps from Rm to Rn, and then I'm just going to apply this result. Okay, and then instead of taking a derivative of f, I'll take a derivative of like f pre-composed with a chart, post-composed with the other chart. And so everything will be the same.
Oh!
Right?
That's why I was getting confused. I didn't realize. Okay.
These are
Okay.
for now open sets in Rm and Rn.
More like sine phi.
When we
Okay.
do it for manifolds, we're just gonna add charts, and in charts it's going to look like the Jacobian of the function in the charts.
There we go. That's fine.
Of the map in the charts.
Yes. Thank you.
Yeah, okay. Can I
Yeah.
erase? Yep. Okay.
I'll go quick on some suggested exercises. It's good to like just compute some derivatives. It's relaxing once you figure out how it works. It requires no effort.
Okay. So yeah, as I even said, so now we let f be just some smooth map between manifolds, and then we pick a point in the first manifold, and then like by smoothness, there exists like charts phi u such that p is in u, and then this is of m, and then psi v such that f, the image of u under f, is a subset of v, it's a chart of n such that our composition psi of f of phi inverse is smooth. And so here's what I'm going to do. We're going to define f tilde as just this, okay, as this composition. And then we're going to think about d f tilde at some point, at some point like u equals phi of p. And then my claim is that this is going to be equal to, let's see, d, yeah, psi at, oh gosh, at like f of p composed with d f at p composed with, and I'm going to write this like this for now, d phi inverse at u. Yes.
What's the notation on the left side of the equation?
The left side of the equation?
F tilde.
This is just of some u where u is some like phi of p for some p in m.
U is a point.
Yeah. Yeah. So this is, yeah, let's prove this for now, and then there's like a nice little thing that you can do with this last little bit. So yeah. So let v belong to t at u of phi of u. This is an open subset of Euclidean space. And that's, again, f tilde is a function between open subsets of Euclidean space. We know how to, we know how it looks in coordinates. So we pick a vector, and then we apply d f tilde at u of v, and this is equal to v of some function. I suppose it would be good to write that function down. G, v is equal to, again, the pullback g of f tilde by the definition. We expand this, v of g of like psi of f of phi inverse. No, I don't like this actually. Yeah. We're just gonna like imagine the function here, because the stuff that I'm gonna do might not work if we have the function in there. So yeah, you have this function, and then here's what I'm gonna do. We can just take this out by doing d phi minus 1 of u of like the function that takes g to like v of g. Yes, is that right? That is right. Of psi of f. And then we can keep decomposing. Df of p d phi minus 1 at u of like this of like g to v of g of psi. And like the reason why I don't want to write g here is because these g's are all from like they're different. They're defined on different domains, so that's why it's a little tricky. But then you decompose it one more time, and then you get like what you expect. Yeah, of like g to v of g, which is just v. Yeah, I'm gonna just one quick thing. So observe that d of
Hold on,
actually, yeah,
How are you doing?
it's kind of it's
How are
like
you doing DFP?
it's like
By DF, all right. By DF, you mean not the Jacobian, the original, the new definition.
the new definition. Yeah.
Okay, but sure. The point is that the Jacobian, in if you write this in coordinates, so you take after you pre-compose things, then in coordinates it just looks like the usual Jacobian of this thing in coordinates, following that same argument. Yeah.
Yeah.
Sorry. What point were you trying to make with this?
Well, just like essentially, like this works. And this is like a straightforward proof that it does.
Okay. Yeah. Sure.
Yeah.
That makes sense.
I guess one little point that I'd like to make is that if I have like a diffeomorphism, like phi, for example, is a diffeomorphism, by the way. It's because it's like a chart, so it's like the most obvious diffeomorphism. So if I have a diffeomorphism, let's say G, and I take dg like at some point p, then in fact the inverse of that is.
Could you? I didn't realize. Could you rotate the phone?
The phone? Yes. The inverse of this function is going to be exactly dg inverse at g of p. And the reason why is because like this is just if you take.
What is the reason why this works? Why is the inverse of the Jacobian of the inverse of the function is the same as the inverse of the Jacobian? Yeah, like sure. Like the point is like if I have a direction here, this direction here gets mapped to some direction here by the Jacobian. If I went back and kind of going in this direction should correspond to having been going in this direction to begin with. So it should just be the inverse of the linear map if G is a diffeomorphism. So it kind of maps every direction to every direction.
There is a very obvious way to see this if you use the definition.
Yeah.
Because it maps v to like
That's true.
v of g inverse composed with g.
Yeah.
Which just cancels out.
Yeah. So if you took G composed with G inverse and the dg of that, the d of that, you should get the identity.
Okay. I shouldn't. Well, it's fine because this is still here. Yeah, and so like we can write this last bit as d of phi at p inverse. These two are the same thing. Okay, that's wonderful. We are done with tangent maps. We still have 2 more topics to go.
You got time, right?
Yeah, we have about 15 minutes.
15 minutes?
Yeah. I mean, you can define what a vector field is in that time, and I think that should be.
This is a tragedy. Okay.
Yeah, that's okay. I knew this would happen.
Okay, can I erase this? Yeah, okay. Okay. So yeah. So a vector field.
So, motivation. Why would we want to? Before, we just had like vectors at a point. Do you agree? Now we want to define something that, what if you had like a bunch of vectors all at different points, right? So you can have a vector field. So at every point you put a vector. Yes.
A manifold has many points.
Yes, because a manifold has many points. What if we put vectors at many points, and we did it in some clever way, or some nice enough way? Yes.
We've like for every like point we've defined atlases at like the manifold. Is there some
Not for every point, for every
no,
open
we
set.
took a point, yes, but then we need a lot of atlases at like every point on the manifold. Is there like a really nice way to like, instead of going through all of this in a
Well, what do you mean by atlas? I just need an atlas and an open set.
No,
I have
sorry,
one
the charts.
atlas?
The charts.
Yes,
Like-
if I have a chart for an open set, right?
Yeah.
I don't have a chart for every point. I have a chart for an open set.
Yeah.
For part of the manifold.
Mhm.
So if I have a chart for a chunk of the manifold, then okay, I can talk about tangent vectors at every point there, because at every point they will all look kind of similar as like these partial xi, just at a different point in the coordinates.
Yeah.
Okay. In fact, actually, this is something we didn't say. Is that if you look at the tangent space, TPM, and take the disjoint union over all the points P of all of these tangent spaces, that's actually itself a manifold. You can give it a manifold structure. Why? Because if I have a chart on the original manifold, right, to Rn, that immediately gives me a chart to R2n, where all the derivatives I just identify with just vectors in Rn. Right? We showed that a tangent vector is some. We showed that a tangent vector is some differential operator AI partial xi. So to specify in a coordinate chart a tangent vector, I just need to tell you what the AIs are. That's just n numbers.
Yeah.
So this means if I have a chart for the manifold, I immediately get a chart for like the tangents, like the combination of all the tangent spaces, where the first few coordinates tell me the point I'm at, and the second few coordinates tell me how to differentiate it up. Yeah. So tangent spaces are actually manifolds. I just kind of cut Ife off before she could say that last time, which is my bad, but we're running kind of late.
So we need the 2n manifold.
Yeah, that's it. To double the dimension.
Particular name?
It's called the tangent bundle, and we'll maybe. I don't think we'll talk about bundles, but whatever.
Unfortunately. Anyway, yeah. So, yeah, we have essentially a collection.
Yeah.
Yeah.
So I'm gonna just. So you can start writing. I'm just gonna kind of spoil everything.
Okay.
We're going to define this thing called a vector field, which is going to let me put a bunch of vectors at many points. And then I'm going to do the following. Suppose I'm standing at a point. Right below me, I see a vector. So if you're walking somewhere and you see an arrow, you want to walk along that arrow in that direction. And then I take a step, and I arrive at a new point, and there's a new arrow. And I can take a step forward in the direction of that arrow. And I can again keep doing this. Do you agree? And the hope is my arrows are nicely coordinated amongst themselves, so that I can kind of keep walking along them and trace out some curves. And this is precisely, just solving an ODE, like an ordinary differential equation. But we'll see that in a moment. So the goal is we're going to have a bunch of arrows at a bunch of points, and we're going to try and follow them and go along these arrows. And we're going to come up with a bunch of definitions to describe that. Yes.
Okay. So yeah, so we have like this collection of tangent vectors at every point, and we want them to like play nice in some sense. And the way we do that is by requiring that for every function, the essentially like the derivative of that function at a point with respect to the direction of the tangent vector is a smooth function. So
So the derivative is smooth, where smooth is in terms of which point I pick.
So like when you're saying we stand at this point, I walk in a direction, that direction should be smooth.
The direction should change smoothly. The direction in which I'm going should change smoothly and like not too sharp.
For any point on the.
For any point on the middle. That's right.
Yes. Yeah. And so like this function right here is written x, and it's a smooth function, or not. It's a function that takes smooth functions, and then gives you smooth functions, and it's like essentially like the derivative, kind of.
So remember, before we had a derivative at a point was I take a smooth function, I give you a number. Now I'm saying let's define something where it lets me take smooth functions kind of at every point. So then it takes in a smooth function and it gives you another smooth function. Because now it's like I take a derivative I know what the derivative is at every point, and that's itself a smooth function. So that's it. Alternatively, if we spoke more about what a tangent bundle is, so like thinking of the tangent spaces as the total collection of tangent spaces as a manifold, you could just say that a vector field is some nice enough map some smooth map that satisfies like one property from the manifold to its tangent. But okay, we haven't developed that language. Well, we have. I've just said it. Maybe I should write something down.
Okay. Yeah. And then the set of all such, such functions x is denoted x with like a bar in the middle of m.
Can you get a different piece of chalk? Because that one's very light.
Yeah.
There's also like my nicer chalk in the. No.
It's fine.
In the other one.
In the other one? It's
The one
fine. It's whatever. This is good. Okay. So, recall from the beginning and from last lecture that our differential operators are only differential operators, or they're differential operators if and only if they satisfy the product rule, right? And so we can give an equivalent definition where this x bar of m is like the set, and in fact the space, because it is a vector space, because it's like you can quite easily see that this x is linear.
X are linear maps.
Because each xp is linear, so like, they're differential operators. Differential operators are linear. And so it gives you a vector space. And so you can define it like this, or you can define it as the space of linear maps. X from smooth functions on M to smooth functions on M, satisfying let's see.
Linearity and product.
Well, linear maps by
Oh yeah.
satisfying the product rule. X of f times g is equal to f times x of g plus x of f times g. Product rule. Yeah, exactly. Let's see.
So maybe make a brief comment as to how they look in coordinates. Just write down the equation.
Yeah. So again, recall that we have, x of p is equal to some like set of coefficients ai. Sorry?
Yeah, that's fine.
Yeah. Okay. Yeah.
Is the vectors field defined locally or
On the entire space.
On the entire space.
On the entire space. For every point, you have a tangent vector.
Yes.
xp takes like a
So at
function.
every point, you know how to take the derivative. So you have a linear map that takes in an infinitely differentiable function and gives you like its derivative at every point, which is another infinitely differentiable.
Oh, so that's what I'm asking. Like, is x the vector field or x of f?
X is the vector field. X of f is I've applied the vector, I've differentiated the function at every point by x, and I got x of f, which is the derivative of the function along x at every point.
If you think of like xp of f is kind of like f prime of p, and then x of f is like kind of f prime, just like as a function.
Yeah, but the difference is now that x is, I'm not just taking a derivative, I'm taking a derivative in a particular direction.
Yeah.
And I have like, I could be taking derivatives in different directions at different points.
Oh, God, I should stop.
That's okay.
It's fine.
So the point is, before, a vector field at a point was just some AI multiplied by derivatives. So it was some differential operator like this. Now that I want a smooth vector field, now that I want the vector field, so I want to be able to take derivatives at different points, I now let my coefficients AI to depend on the point P. And otherwise it looks the same. So in a coordinate chart, a vector field is some differential operator, which is like AI of x times taking a derivative at x I. So like the coefficients can change. So this meaning that if I go from one point to another point, I could be taking a derivative in a different direction. But to make this smooth, I want AI of p to be smooth.
Exactly.
Depending on the point.
Yeah. So these coefficients, you can think of these kind of AIs. They depend on p, right? Because x of I or
They just
xp.
tell you the direction in which to take the derivative, and now I just let them change.
Yeah.
Let them
So yeah, the coefficients must change smoothly with respect to.
In the last 5 minutes, let's just quickly define flow.
Oh my God. Okay, fine.
Forget about the complete vector fields. Well, whatever. Just define flow.
All right. I'm gonna erase this. Okay. So essentially, I'm gonna try to do as much as I can. So suppose you have a vector field. Suppose you have some kind of vector field, and a natural sort of thing to think about is, okay, let's say I pick a point, and then I want a curve that is sort of tangent to the vector field at every point. Or specifically, I want like gamma prime of t. Well, if this is p, I want, first of all, that gamma of 0 is equal to p. And I also want that like gamma at every point is going in the same direction as the vector field at that point. So gamma prime of t is equal to x at gamma t. So it turns out that for both in Euclidean space, if you have like a vector field, then it has a unique curve that satisfies this differential equation with these initial conditions, and you can translate that result to manifolds as well. So if I have a vector field x, then I'm going to have like a unique gamma from J to M such that like gamma of 0 is equal to P, some fixed P, and then gamma prime of T, which we defined as like, you remember the tangent map stuff that we did with gamma? It's defined in a similar way. It's essentially, it's quite literally the same thing. It's ddt.
So it's what I was saying. You have some set of directions at every point. Then, if you start at a point, you can like follow these directions and get some path, and that's all it is.
Yeah.
And if you have a vector field, so maybe at this point I'll just say, if you have a vector field, write down the definition for flow like phi TFP, and then
Okay.
I'll just say stuff while you're writing.
Yeah.
So suppose I'm given some vector field x, then I can define the following map. It takes in a starting point, and then it takes in a time. So, and it outputs a point in the manifold. And in what way? It takes in a point in space P, that's where I start at. Then the time that it takes in is how long should I flow along the vector field starting from that point? And then the output is where do I end up? Okay? And that's what's called flow along the vector field x. Starting the flow for time t along vector field x starting at point P. And usually people denote this with like a capital phi with like a T and a P somewhere. So I start at a point P, I flow along the vector field x such that I'm tangent to it for some time t, and end up somewhere. And where I end up is this phi tp. And this is defined uniquely for some small time, for at least some small time. There are some cases where actually like you can have a vector field defined on a manifold, but you might not be able to flow along the vector field for like an infinitely long amount of time. Because you might like fly off the manifold.
Yeah.
Like you can have a vector field that tells you to like take bigger and bigger steps, and in finite time it essentially asks you to take an infinitely large step.
It's like
and then because
like let's say this is a smooth curve, but then
yes.
it goes to like, there's a discontinuity.
Yes, and there's a common example that we'll show, but in most cases we'll consider you will have that actually on nice enough. You can have nice enough manifolds where you kind of can't fly off the manifold, and there every smooth vector field you can flow along the vector field for as long as you like. Okay. Big important property about flow along a vector field is, suppose I start at point P and I flow for time t plus s. Okay, I end up at some other point. That is the same as starting at point P, flowing for time s, and then starting there again and flowing for time t. Okay, that makes sense? And this follows from the fact that flow along curves is unique. Yes.
It does.
And so this is like, yeah. And then there's other things to say about this, but I think they'll be said next.
Remind the 247.
247.
Yeah. Okay. This was great.
I think that's it. Okay.
Yeah. Let's stop.
Yeah.
Sorry,
No,
Just kind of set
it's,
the last bit, but just
it's
the
fair. That's fair.
Um,
Okay.